For years, front-end development operated on a simple one-to-one relationship. A user clicked a button in the UI, and the application executed the intent. Today, that single user intent has to be reachable from multiple places. Users expect to trigger that exact same filter operation from a dedicated toolbar, a custom keyboard shortcut, and a searchable command palette. And the demands have expanded beyond human interfaces. That operation now needs to be invoked by an AI assistant composing a multi-step workflow, an external agent connecting via the Model Context Protocol, and an automated end-to-end test suite. This diagram shows the structural crisis. Core actions on the left connect to multiple surfaces on the right, generating an N-by-M integration matrix. Without a shared abstraction, teams duplicate metadata for every single action, writing a UI label, an AI schema, and a test validation rule. Maintaining these separate definitions guarantees schema drift. Bugs multiply as the surfaces fall out of sync. Eventually, the cost of integration halts development. High-value features like macro recording are abandoned simply because wiring them up across the application is too expensive. Solving this requires converging on a shared, schema-driven primitive. Platforms like VSCode, Figma, and Linear have independently arrived at the exact same structural solution to this problem, the command dispatch architecture. Multi-surface applications do not actually suffer from an integration problem, they suffer from a structural abstraction problem. To scale, the application must isolate the operation into a single primitive that all surfaces can consume. To build this architecture, we replace the tangled integration web with a clean hub-and-spoke model, constructed from 3 interlocking primitives. The first primitive is the state model. This involves taking your existing state management stores and wrapping them with strictly typed interfaces. This schema is the single source of truth, ensuring any operation validates against a strict contract. The second primitive is the command registry. Sitting directly atop the state model, it acts as a centralized map connecting string identifiers to specific behaviors. The core mechanism here is the dual registration model, a pattern heavily utilized by VSCode. It strictly separates declarative metadata, like labels and rules, from the imperative handler that performs the work. This separation solves a major performance bottleneck. A command palette can eagerly load thousands of lightweight metadata records so they are instantly searchable, while the heavier execution logic is lazily loaded only when the user invokes the command. By combining a strict state model with a centralized command registry, you decouple the user's intent from the application's execution. You establish a stable foundation that any external integration can reliably interact with. The third primitive is the schema bridge. This mechanism connects our internal architecture to the outside world, particularly to AI and external protocols. Here, a ZOD schema translates into a universal JSON schema. This single conversion allows Vercel AI SDK to generate LLM prompts, satisfies the Model Context Protocol for external agent tools, and enables the front-end palette to dynamically render UI parameter forms. Because AI uses the exact same schema bridge as the UI, there's no separate tool definition. This eliminates the risk of AI hallucinating parameters based on outdated or misaligned documentation. The automated testing suite hooks into this pipeline, using the schema to generate strictly typed fixtures that compile test intents down to specific execution adapters. The schema bridge fundamentally changes the economics of software development. You define the parameter schema perfectly just once, serving the UI palette, the AI assistant, the MCP server, and the test suite flawlessly. Looking at the actual code, we see how these concepts converge into a single command object interface. This TypeScript definition highlights the strictly required properties: an ID, a human-readable label, a typed schema, and the execution function. To manage this registry effectively, we apply the principle of command-query separation. Every command is explicitly categorized as either a mutation or a query. Mutations are operations that fundamentally alter the application state, like applying a filter or rapidly deleting a record. Tagging them explicitly allows the registry's middleware to automatically capture reverse state patches for undo systems and log execution for telemetry. Queries read the state without side effects, like computing dataset statistics. Language models rely heavily on these query commands to understand context before composing multi-step mutations. But there is a specific risk here, known as the inner platform effect. As the registry grows, there is a temptation to add conditionals, loops, and complex inheritance hierarchies directly into the metadata. The architectural boundary must be strict. Command metadata is data, not code. Any conditional logic regarding execution belongs exclusively inside the imperative execution handler. Enforcing this boundary keeps the command object flat and strictly defined. That discipline prevents the registry from mutating into an unmaintainable God object, collapsing under its own weight. The primary hesitation teams have with new structural patterns is the fear of architecture astronaut syndrome, building elaborate infrastructure that requires a massive, system-breaking rewrite. Achieving multi-surface capabilities does not require you to rewrite your application into a full event-sourced architecture. Instead, you can adopt this model incrementally using the Strangler Fig pattern. In Phase 1, you wrap the existing codebase. You create a thin command layer around your legacy state actions, registering them with basic IDs and labels without altering any of the underlying execution behavior. This initial wrapping delivers immediate value, letting you deploy a command palette on day 1. In Phase 2, adding formal schemas automatically wires those commands into the AI assistant and the MCP server. Phase 3 is extraction. Once the commands are routing smoothly through all interfaces, you safely move the business logic out of the legacy stores and directly into the new command handlers. This migration strategy forces a reevaluation of the traditional rule of 3, the heuristic that you shouldn't build an abstraction until you have 3 concrete use cases for it. The command dispatch architecture alters the economics of that rule, because formalizing just one command immediately serves the UI palette, the AI assistant, the test suite, and the macro recorder simultaneously. The threshold for a valuable abstraction is met the moment it is written. The command dispatch architecture provides the structural foundation for modern software. It transforms multi-surface integration from a compounding liability into a highly scalable asset.